Good day everyone. In this video, we will talk about computer architecture and computer organization, the arithmetic logic unit, and also the control unit and binary number system. So to start, let us define what is a computer architecture. Computer architecture is composed of two words, computer and architecture. So when we say computer, it is an electronic machine that is used in order for us to process our inputs and generate an output. So those output may be a file, a music, or a video, and we could also use computer in order for us to communicate with other people, some office works, and generate some reports. So it has a lot of usage. So the user utilizes those resources from a computer. So in order for them to carry out the tasks that are assigned to them. So when we say architecture, as I search through the internet, says here that the architecture is the art of practice or practice of designing and constructing buildings. So if that's the case, computer architecture is all about the art of building the computer. And when building the computer, we always ask ourselves how much memory should I put into this computer and which type of instruction set should I use in this computer. So when we ask ourselves how much memory, we always wanted to have a much higher memory in order for us um, to carry out or cater some information to our computer. So when we say memory, so those are the random access memory or the RAM. So it's the one that holds the processes in your computer. So the higher the RAM, the more processes it could manage. Okay, and then which type of instruction set should I put or should I use in this computer? So those instruction set are the predefined instructions, which is used by your computer in order for the software level communicate or to communicate the software level to the hardware level. Okay, so in our computer system, there are two types of um, or there are two categories of parts of a computer. It's the software and the hardware. So the software are the applications that you use in our computer. So you can see it in on your screen. So let's say some applications like YouTube or Facebook, or let's say Office, Microsoft Office. So those are the software, so applications from your computer. And then when we say hardware, those are the parts of the computer that you could touch. So for example, mouse, keyboard, what else? The components inside the computer. Okay, so those are the parts of the computer. Okay, so if that's the case, what is computer organization? So the most commonly used definition of computer organization is the computer organization is the way the hardware components operate and they are connected to each other. So meaning to say, it's just like giving a hardware its purpose or responsibility inside the computer system. So for example, in a computer organization, the input devices are the hardware that accepts the input. And then of course the processors, the one that process, the IO devices, or let's say the output devices are the ones that generates the output or the one that displays the output once the informations from the users are processed by our computer. So there is a sequence of operation to be executed by our computer system. So there's an organization. There's a system or systematic way of operating inside your computer. So that's the organization. Which one should come first? Which hardware should come first, or which of this hardware should do this task? Okay, so there's an organization. So there's a designated part of the computer that should um, that should do this task. So it is composed of the I/O devices, memory system, and a processor. So in summary, the processor is used to solve mathematical problems. So memory is used to save all the processes or those processes, and finally the input and output devices to interact with the processor. So this is just a simple calculator. So for example, we entered 5 and then plus operation and then the 7. So this mathematical equation here will be solved by our processor, then save the result to our memory before the output so that we could retrieve the result and use it later on. So for example, 7 plus 5 is 12, and then we want to add more values to 12. So since they are, or since it is saved in our memory, we could still retrieve the result from the previous operation. Okay, so there's a purpose for each hardware component. Okay, so in figure 1 it shows how these parts of the computer organization works together to finish a task. So the user enters some value and the arithmetic operation, and then the processor will store it to the memory. So what are the examples of input devices? Those are the mouse, keyboard, microphones, and cameras, and many more. Okay, so after getting all the input values, the processor will start solving it one by one by saving and retrieving it from the memory until no more operations left. So after solving these equations, the processor will retrieve the result and pass it to the output device for display. So what are the example of output devices? Those are the screen from our computer, printer, speakers, and many more. Okay, so those are the output devices. So let us talk about what is an arithmetic logic unit. An arithmetic logic unit is a part of the processor that performs mathematical and logical operation. So it is a digital circuit and a fundamental building block of a central processing unit. Okay, so it is the one that solves all the um, mathematical and logical operation. So when we say mathematical operation, it is the addition, subtraction, multiplication, and division. And when we say logical operations, it is the AND, OR, and NOT. Okay, so we will discuss more about it on our next slides. So here is the block diagram of an ALU. So consider an ALU having 4 arithmetic operations and 4 logical operations. So to identify one of these 4 logical operators or arithmetic operations, we will use 2 control lines. Okay, so this is just an example for you to understand how ALU works. So let's say we have 2 control lines, C0 and C sub 1. So these control lines will determine which operation is to be used for the input registers A and B. Okay, so for the possible values for control line 0 and control line 1 are 0 and 1. So when we say 0, it is an open circuit, and for the value 1, it is the closed circuit. Okay, so what is the meaning of that? We all know that computer is composed of wires and transistors. So meaning to say, the value of C sub 0 and C sub 1 depends if these wires or circuits are open or closed. Okay, so for example, it is an open circuit. So I mean to say there's no current or electric current that flows on that circuit. And let's say closed circuit, meaning to say it is closed. So I mean to say there's a electric current passing through the wires. Okay, so this is just an example to give you an idea how ALU determine what operations to be used to solve for input registers A and B. Input registers contain an 8-bit binary number. Okay, so everything that is processed, or let's say when you type a symbol or character on your computer, it is translated into binary number. Okay, because computers can only understand binary numbers. And in order for us to represent a character or symbol to our computer, um, it can be represented by an 8-bit binary number. So meaning to say, the letters here or characters has an equivalent value for an 8-bit binary number. Okay, so here let's say we have an input in our input register A, we have assigned an 8-bit binary number. Same goes for B. And we have an output register C. So the operations to be used for A and B are determined by the values of C sub 0 and C sub 1. So if C sub 0 and C sub 1 has a value of 0 and 0, so therefore we will add the value of B to A. If C sub 0 has 0 and C sub 1 has 1, we will deduct the value of B to A. If C sub 0 has 1 and C sub 1 has 0, then we will just flip the value of B, okay, using the NOT. So this is a logical operator, the NOT. So we will know more about this later on as we process this inputs from our registers. Okay, and then C sub 0 and C sub 1, if they have 1 as their value, so we'll just add 1 to our input register A. Okay. Okay. So for our first control line, so control line 0 has 0 and control line 1 has 0. So therefore, we will just add the value of B to A and then assign it to our output register C. So how are we going to solve for an 8-bit binary number using addition? So if these are the values inside the input register A and B, so we'll just add them together. It's just a simple math. So 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 0 is 1, and 0 plus 0 is 0. Okay? For the next one, we will just deduct B to A. So this is the answer. So in order for us to solve this, so 1 minus 0 is 1. 0 minus 1 is 1. So how did it happen? So we will just borrow 1 from the next cell. So we'll just transform this into 0. And then this one into 1, 0. Okay. So let me draw first a table in order for us to understand why 1, 0 represents the value of 2. Okay, so here we have our table. So we have here 7 cells or columns. So 1 or 8, 1, 2, 3, 4, 5, 6, 7, 8. And then from 0 up to 7. So we use the base 2 since we have 2 possible values for binary number. It's 0 and 1. So I mean to say this 2 here signifies the possible symbols of a number system. So once we raise this to n, and n represents the value of the place value here, so 0 to 7, so we will get this decimal values. Okay, so 2 raised to 0 is 1, so anything that is raised, or any number that is raised by 0 would result to 1, so that's why 2 raised to 0 is 1. 2 raised to 1 is 2. 2 raised to 2 is 4. 2 raised to 3 is 8. 2 raised to 4 is 16. 2 raised to 5 is 32. 2 raised to 6 is 64. And 2 raised to 7 is 128. Okay? So in order for us to prove that 10 is has an equivalent value of 2 to decimal, so we will just plug in 10 to our table. So from left, so 0 to our first cell here, so this is 0, and then 1 to our next cell. So 10, 10. Now the next step is to multiply 1 to 0. So 1 times 0 and 2 times 1. So this would result to 0 plus 2 times 1 is 2. So 2 plus 0 is 2. So that's why 10 represents the value of 2. So this 10 here, in binary, it's 2. Okay, so if you convert it to decimal. So 2 minus 1 is 1. And then 0 minus 0 is 0. 0 minus 1 cannot be. So it's just the same as this cell here for this case. We will just borrow 1 here. So this would become 0. And then this 0 value here would become 1, 0. Because it turns into 2. So 2 minus 1 is 1. And then 0 minus 0 is 0. 1 minus 0 is 1. 1 minus 0 is 1. And 0 minus 0 is 0. Okay? Next is not B. So since this operation only focuses on B, we will just ignore A. And then we will just flip the value or turn the value of input register B. All zeros would become 1 and all ones would become 0. Just like this. And then assign it to output register C. And then for the last one, we will just add 1 to A. So we will just ignore input register B. And then the next one is, since we will just add 1 to A, so this is the value of input register A plus 1. So that the result would be something like this. So 1 plus 1 is 2. And we all know that 2 can be represented by 1, 0. Okay? And since each cell could only contain one symbol, it's either 1 or 0, so we will just retain 0 to the first cell. And then this 1 here would become a carry. So this 1 here would become a carry to the next, or we will carry 1 to the next cell. And since the next cell is 0, 1 plus 0 is 1. And since the plus 1 here in our input register A reflects on the second cell, so we'll just it will not affect the other or remaining cells. Okay, so we'll just bring down 1, 0, 1, 1, 1, and 0. Okay, so here are the things to remember. So aside from ALU and registers, processors contains a control unit. So what is this control unit? A control unit is responsible for sending electrical signals to the ALU memory I/O devices and directs the operation of a processor. So control units gives commands to the ALU which operations to be used on the data, and the ALU stores the result to the register. So processors may use one or more ALUs and retrieve data from the register. A register is a storage with a small amount of memory, and it is also a part of the processor. Okay, so it resides in our processor. So a computer processes instruction using a language called binary. And then all information in a computer is stored and operate as binary numbers, or 0 and 1, and is manipulated by transistor switches. Characters, symbols, or numbers have an equivalent set of binary numbers, and one character is equivalent to 8-bit or 1 byte. You can also refer to ASCII table below, which is downloadable or searchable to the internet in order to see the equivalent binary value of the alphabet or other symbols. So it looks something like this. So for example, we type J to our word processing software, or let's say in our notepad. Our computer sees it as a binary value. So J is 01001010 in our computer. Okay? Say for example, capital L. So L can be converted or has an equivalent value in binary as 01001100. Okay? So ASCII table, the ASCII stands for the American Standard Code for Information Interchange. In summary class, a computer uses processors to solve mathematical and logical problems, specifically an ALU. The user can interact with the computer using input and output devices. A computer understands a language called binary. The ALU, CU, and registers are parts of a processor, and ASCII table provides an information about the equivalent binary values of a character, symbols, or numbers. And that's all for now. Thank you for listening.